Let's talk about testing hypotheses in statistics. And this idea is not just important for statistics, but the world around us. For example, think about a court case where someone is presumed innocent until there's evidence of guilt. Well, what are the outcomes of these court cases? Well, they can go many different ways. Because what we're looking at right here is there's a starting belief. And that starting belief is a null hypothesis. So when you think about what you believe initially, without any evidence needed, it is your null. Think about null, it means nothing. You don't need anything right now to change your mind. This is what you currently believe. You walk into the court case, you believe someone's innocent. You would need evidence, and you would learn that throughout the court case to change your mind to an alternative. You're asking, can you change my mind? What can you present to me with data that leads me to believe otherwise from what I currently believe? And when we do this in statistics, we state the null the following way. This reads on the bottom of the screen, the null hypothesis states. Always read H sub O that way. It can be read also H naught or H null, and that is the null hypothesis states that the population parameter, the thing we want to understand, is equal to some hypothesized value. Now, I know it's crazy to believe to start that some hypothesized value is currently equal to something. But that's just an initial belief. We don't need any evidence for it. It's just what we believe. The null needs no evidence. And we always use, at least for these first two chapters, an equal sign. So think about what we can do right here. Well, we could believe that the true proportion is equal to something. And what we believe it's equal to actually goes with the sign of the null. We put right here P naught. So the true proportion is equal to some hypothesized proportion. I could just say, I believe 80% of students love Taco Bell. And that would be read, my null hypothesis is that the true proportion of students who love Taco Bell is equal to, and P naught is going to be 80%. Once again, that would be the value of P naught. We can do it with means also, where we want to know or we believe something about the true mean, and what we believe is that it's equal to some hypothesized mean, mu naught. And so I could say, it is my belief, currently my null hypothesis, is that the true mean age of UT students is equal to 21 years old. I don't need backing for that. It's just a belief I hold. You can present evidence to me to convince me otherwise, and we'll look at alternatives here in a second. Lastly, with this format, we will cover the difference between two means, mu1 minus mu2. Those are mu's right there, mu1 minus mu2, and that, we'll put a little divide between these, so you can see this are the hypothesized values. Usually we hypothesize that is equal to 0. This one has a slightly different notation, delta naught right there, difference kind of change in. But in our class, we will use 0, and you can use other values. You can hypothesize it's equal to anything. I think the difference between these means is equal to 10. Well, we could test, Florida students and UT students, give them a math test, and we would say, well, I believe that the true difference between UT students, put a little mu UT right there, and mu Florida, there's our first and second. You can call them 1 and 2, or UT Florida, and mu UT, mu Florida is equal to 0. There is no difference. And once again, we could test a difference, but most of the time when testing two means, we assume the difference is equal to 0. I want to point out, once again, that a huge thing to know is that whenever you are testing things with the null, you write this notation, the null has the equal sign. And we have pairing right here between these, where mu would be with mu naught. P would be with P naught. And then when we would do difference right here, we'll do it slightly different color. The difference between two means, a lot of times we use 0. Writing the null hypothesis is very important, and choosing between P, mu, or mu1 minus mu2 would depend on if you're doing proportions for P, mu for means, and mu1 minus mu2 for the difference between two means. Make sure to read the question. This gets into, what is this alternative hypothesis? Well, it's what someone's trying to present evidence to us for. So we believe someone's innocent in a court case, and if they come in, they don't say anything, and no one says anything, well then, I would still believe they're innocent. This goes to key terminology we use. We didn't prove they're innocent, we just still believe that. I prefer words like still believe or do not reject their innocence. Classical statisticians will say words like fail to reject. Think of what fail to reject means. You either go to the mall today or you don't go to the mall today. You either go to the mall today or you fail to go to the mall today. You either reject the null or you do not reject the null. You either reject the null or you fail to reject the null. Fail to reject just means did not do. So I prefer in modern language, which I wish statisticians would catch up to this, just to say, I don't reject that. I still believe it. That's what don't reject means. A bad word to use is accept. Accept also sounds like it's true. You will hear people say that, but I'm against using the word accept because it's almost like we've finalized our thoughts on it. I accept this is true. No, we just can't reject it. It's believable. That person who came into the courtroom and nothing was said, no one gave evidence against them, well, it's believable that it's true, that they're innocent. I don't accept that they're innocent. I just don't have reason to believe otherwise. Statisticians talk a little bit weird. So a key thing to know right here is we're trying to understand what the truth is. Just like that court case, we're trying to understand the truth of their guilty or innocent nature. So how do we write the alternative? It's super easy if you've practiced writing your null. You just change the sign. The only difference between the alternative is one of three possible signs. And this is what you're trying to show evidence for. Maybe I want to start my Taco Bell campaign. I believe currently that the true proportion of students who love Taco Bell is equal to 80%. What is 80% again? Well, 80% is P naught, because it is the hypothesized proportion that I believe. Maybe I want to show evidence, and remember, evidence is always related to the alternative, that love for Taco Bell has increased across UT. So what would I want the alternative's sign to be to show evidence that love for Taco Bell has increased? Well, the alternative, which is red, the alternative hypothesis, that's how H sub A is read, is I wish to show evidence for the true proportion of UT students that love Taco Bell increased. We don't put an equals underneath this because that would actually converge with the null. And we really are just going to believe after this that we are going to retain the null, still believe it, fail to reject it, or we're going to show evidence for the alternative and reject the null hypothesis, which is where we're going to go with our test. So make sure to look to not the data. This is not what we do. We do not look at the data for the sign of the null. We ask a question. Just think about how researchers do this. The first thing they would do when they have thoughts on what they want to research is write their research question. Then they collect data. You don't collect data and then look to find results in the data that you weren't looking for. This is actually called p-hacking. If you look too much for results, you will find them because things that are statistically significant occur 5% of the time, or exactly 5% of the time, p-value is less than 0.05. And by searching through data repeatedly, you will find something. So if you go and try to find significant p-values, you can find them with enough data. And that's why you're just hacking p-values to find them. And it's not a good idea. It's bad statistics. There's corrections, like the Bonferroni family-wise correction for the corrected alpha level. Not gone into in this lecture. I love statistics. There's always a way to fix things when people do bad statistics. And so what we have right here is we have somebody, let's say, believes that 20% of students at UT use the T-Rex. And someone says, I don't believe that. I think it's different than that. So this was the initial belief that doesn't need evidence. It's what someone believes. And someone says, well, change my mind. Show me that it's not equal to that. Because they're looking for evidence that the true proportion of students who don't use T-Rex, and remember how this is read, I believe currently that the true proportion of students who use the T-Rex is equal to my hypothesized value, 20%. You are trying to show me evidence for your alternative that the true proportion of students who use the T-Rex is not equal to this. Now you need to collect some data and show me that, because I'm not going to change my mind until you show me some data. What they see is they collect a sample, and in their sample they find 17%. Maybe they talk to 100 students or 200, so 34 would have to be the sample, the successes, and then you could divide this by the sample size. I just made this up for this problem, pretending that this is the sample proportion right here from data. What we would do then, if we are doing the does not equals test, is we would do both sides of the curve. The does not equals test would plot where we landed at 17, and then something just as extreme, and the p-value is going to be the sum of the areas on the outside. Now, what's important to note is p-values have a very specific relationship. When we plot p-values on a curve, it depends on the sign of the alternative. If the alternative is a greater than sign, we plot to the right. If it is a less than sign, we plot to the left. Making these p-values, if we look at them in output, if this is 10%, this would have to be 90%. The does not equals alternative is done by taking where you landed and reflecting it on the other side. The does not equals alternative is always double the smaller. Take a look as best I could draw. We would simply reflect that on the other side. These two down here are complements of each other. And this would be your z-score in this instance of where you landed. So the z-score here would be in the same spot, and output's going to tell you your does not equals alternative, greater than alternative, and your less than alternative, mirror image. And so the p-value has an important interpretation in statistics. It's going to tell us whether or not something was likely or unlikely given the null is true. That makes it a conditional probability. Very important right here. It's not just do we think what we saw could happen, it's given the null is true. So one of my favorite examples to use with students is Brian running track. So I claim to you that my average mile time is 5 minutes. So how would you write that out? Brian claims his average mile time is 5 minutes. Well, we'd write, I currently believe Brian's true mean mile time is equal to 5 minutes. That's a hypothesized value. The mu naught in this instance is 5 minutes. Now, thinking about what could happen right here as we collect data, if you watch me run miles for like a week, you might see, on average, Brian was taking 20 minutes to run his miles. So sad day for Brian, 4 times around the track. And with this right here, it took me 20 minutes each time I did a mile. Now think about this. Is that likely given the null is true or unlikely? Me taking 20 minutes with the claim of a 5-minute mile. And I'm telling you, you go out there and I'm like, that was a good mile. And you're like, that was another 20-minute mile again. You kind of whisper it to yourself so I don't hear it. But I believe that I'm a 5-minute mile runner and I'm making this claim. Was me running 20-minute miles a likely result or an unlikely result? At this point, we don't even need statistics. We know instantaneously that's not likely. You would reject the claim of me being a 5-minute mile runner and say, I have evidence to believe that you are not a 5-minute mile runner. You might be testing simply the alternative. That's an O right there. We should write an A for the alternative, that my true mean mile time is greater than 5 minutes. So you might want to show evidence that the true mean mile time I have is greater than 5 minutes. And if you plot your results, I'm going to be way over here off the curve. And there's going to be virtually no possibility of this being true. But what if it were to take me 5 minutes, 1 second? Now, I didn't run them exactly in 5 minutes, but random variation, and I'm not doing the exact test right here, I'm just talking theoretically, random variation can happen. So is this a believable time? Is this a likely result, given I'm a 5-minute mile runner? Well, it's way more likely than the 20-minute result. So what you'd get right here is we'd probably land close to the center of the curve, a little tiny bit to the right. The p-value would be large. The p-value tells us the probability of our results or results more extreme happening by random chance given that the null is true. Let's put the words in that. This p-value is telling us the probability of Brian running his miles in 5 minutes or more given that he is truly a 5-minute mile runner. It tells us the probability of this given Brian is a 5-minute mile runner. The observed results we would see here might have a p-value about this. So if Brian is a 5-minute mile runner, the probability of him running 5 minutes, 1 second or higher is very likely if he is a 5-minute mile runner. So we'd say this is a likely result given a 5-minute mile runner is actually doing it. So what do we do if it's likely? We'd still believe him. Hey, what you did was likely given you're a 5-minute mile runner. I think you are a 5-minute mile runner because I should see something like this most of the time from 5-minute mile runners, as opposed to the previous example where it took 20 minutes. Then we had the extremely unlikely result right here, way off the curve, which is virtually impossible. Your 5-minute mile runner takes you 20 minutes? That's virtually impossible. I reject that you're a 5-minute mile runner. I have evidence that it takes you more than 5 minutes to run your mile. Very important to know that when we do these tests, there's two conclusions. We either reject the null or we fail to reject the null. Now, when you reject the null, there will be evidence for the alternative, because we're rejecting what we currently believe in light of evidence for an alternative. When you fail to reject the null, you do not have evidence for the alternative. This is why I like to say we either reject the null or we do not. Because you can say do not reject the null. Think about this. If you do not reject the null, you do not have evidence for the alternative. If you do reject the null, so you can say do reject right here, I do reject the null. And if you say do reject the null, you can say I do have evidence for the alternative. So if you reject the null, you do have evidence for the alternative. If you do not reject the null, you do not have evidence for the alternative. You do not have evidence for the alternative. And when do we reject the null? Very important, we reject the null when the p-value is below 0.05. 0.05 is the commonly used alpha threshold. Alpha is simply a bar by which we pick the point at which we reject the null. So here's alpha right here set to 0.05. So any p-value below 0.05 leads to a rejection of the null, and any p-value 0.05 or higher leads to us not rejecting the null. Remember our three alternatives? Well, sometimes this one right here, the does not equals, is called the two-sided or two-tailed alternative. How do we find the p-value on that? Well, we take our result right here, which is the p-hat, in this instance for a proportion, and bring it to the left side. We also put it on the right side, because we want a result as extreme to find the area of something in the tails, down here. The p-value is going to be double the smaller one. So if we had done a left-tailed test, we would get a completely different p-value. These are called one-sided alternatives right here, the left or the right-tailed test. And notice that the p-value is half of the two-tailed test. What about the right-tailed test? Well, you simply go where you landed. Here's where we landed, on the curve right here, the sample proportion, and we'd shade to the right. Notice that these are complements. That you have right here, 0.933 is the complement of 0.067, as in they add up to 1. So what is our reasoning for this? Well, we have some steps right here that we like to do. When we do this, we need to remember that we are writing out the steps, practicing the way we are doing this. So first off, let's write out our null and alternative. What do we currently believe? What are we looking for evidence for? Writing the null and alternative will help you with a lot of problems. The best thing to do is write your null by choosing either p, mu, or mu1 minus mu2. Then know your hypothesized value p0 or mu0. Or if we're doing difference between means, 0. So we'll try to write a mu1 minus mu2 down there for the parameter we are trying to understand. Now, when you do the alternative, you simply change the sign to the researcher's question. The only difference between the null and the alternative is going to be the sign related to the researcher's question. Now we get into actually doing the mathematics and checking the conditions. When we do the mathematics and check the conditions right here, it's going to depend on what type of test we are doing. A one proportion z test is for categorical data. Categorical is in what proportion of students love Taco Bell. And the conditions for this are going to be randomly select students, less than 10% of your students are from the population. And lastly, remember, pause here, because if it's categorical data, we are doing the success failure condition. Now, the success failure condition is always a bit weird, and I'll explain why, because now we're using P0, Q0, and 1 minus P0 is Q0. So both NP0 and NQ0, which are the hypothesized proportion and the complement of the hypothesized proportion, need to be greater than or equal to 10. And if it's exactly 10, don't worry. Why is it P naught here? Well, remember back in the day when we used to do NP and NQ? Well, we'd love to use P, but we don't know it. But the null hypothesis is that the true proportion is equal to P naught. So wait a minute. Going off this, isn't P naught just P in disguise for us currently? And this is not when we do confidence intervals with P hat, but with this, when doing a test, you believe that your null proportion is equal to the truth. So in essence, down here at the bottom, we're just using a proxy for P and Q, because we believe currently that P naught is equal to P. From here, we just have to do the mechanisms to find the mechanics to find the z-score or the t for means. So when we go right here, let's take a look at the math. We have our null hypothesis that the true proportion is equal to some hypothesized proportion. The top part of the equation is just a difference. And you'll notice this throughout all equations we use for z-scores, is this is just a difference, and then we standardize that difference. So right here, we have a difference, and we standardize that difference down below with the standard deviation at this point. It is called a standard deviation because P naught is believed to be the truth. We're not using P hat, which would create a standard error. Very, very small differences right there. I've never tested students over that. It's just a small difference in terminology. Now, what we need to do now is find the p-value. And this is usually where students get stuck. To find the p-value, you need to go to the associated curve. The z is the normal curve. So once you get the z-score, which if you notice, the z-score on this curve would actually be a z-score of 1.5 negative. Don't forget your negative right there. How do I know that? Well, look at the standard deviations. The standard deviation here is 0.02. So if we take 0.02, and then we take the p hat, and then we take the p naught, which is at the center of the curve, we get the equal to negative 1.5. You can also see it visually, especially if you write your z-scores down below on the curve, because we'd go here 0, negative 1, negative 2, and there's where we land at 1.5 standard deviations below the mean. You can also then get some estimates of the p-value, but we preferably would use applets. How do we know which way to shade? We know the way to shade left, right, or both sides based on the sign of the alternative. If it is a greater than alternative, we shade to the right. If it is a less than alternative, shade to the left. Look, it points to the left. If it's the does not equals alternative, then we shade to both sides. And I usually like to draw it sometimes like this, like it's shading both sides right there. So the sign determines the way we shade, which is determined by the researcher's question when we do this. But what about if we wanted to use quantitative data? Well, we could ask questions like, is it true that Brian runs that 5-minute mile? Takes him 360 seconds or 300 seconds, thinking what 5 minutes would be in seconds. 300 seconds? Well, if we did it in seconds, we would say, Brian claims, and he currently believes, that his true mile time on average is 300 seconds. I believe that his true mile time is not equal to that. Notice how I said not equal? Which could encompass that I am faster, you never know. But this right here is what the person is trying to show evidence of that is not equal to that. Notice the steps we did again. The first thing you must do when doing any of this is writing your null and writing your alternative. And the only thing that changes is the sign. This value over here on the right, once again, is the hypothesized value. That is mu naught for this equation. Brian claims this. Well, we say currently, sure, okay, we'll believe that until evidence otherwise. You're a trustworthy person. And now we need to standardize the value. And this goes to the t statistic again because we're doing a mean. I like to say Mr. T is mean. I'm sure he's a super nice guy. He's only mean if you're doing drugs. But Mr. T is mean helps us remember that T is used for mean. So it'll probably be pretty mean if you use the wrong distribution, because he is the one who created the T distribution with William Gossett. And up top, you'll notice we have once again a difference, and that difference is standardized. Wait a minute. Look at this equation. This equation with a difference standardized, and let's write over here to the side, the difference and it's just standardized down below by a standard error. This is a standard error because it is created from a sample, not the truth. This equation looks eerily similar. I'll use the exact same color coding. Taking a difference and standardizing it to create a test statistic of a standardized metric of how far things are away. Same thing. The top part of the equation is how far is our sample from what the hypothesized value is. Sample proportion minus hypothesized proportion. The bottom of the equation just allows us to standardize these differences to put it into a z or a t, which is going to be a standardized unit of measurement of distance away. Down here, you see the sample mean minus the hypothesized mean over the standard error of the sample mean, which is variation, a way to standardize it and understand spread of it, which is found by the formula s over square root of n. Do not forget that every t has with it degrees of freedom. Since we're doing a one sample t, the degrees of freedom formula is n minus 1. If my sample size was 200, what would the degrees of freedom be? The degrees of freedom would be 200 minus 1. What does that tell us? That tells us the shape of the t distribution we are using. So you can see right here in this problem, there were 11 degrees of freedom, which means n was equal to 12, and degrees of freedom would be n minus 1, which is 12 minus 1, which is equal to 11 degrees of freedom, which determines the shape of the t you are using. There are infinitely many t's, and you must know the degrees of freedom for the t you are using to make sure you have the proper p-values when running your test. There are conditions, once again, that when we do a t test, we need to have met to use the t distribution. We need to randomly collect our data. This question says that, we're good. We need to collect less than 10% of the population or change the formulas, because there are corrections that we don't use right here. Lastly, we need to do the nearly normal condition. Now, the nearly normal condition sounds way more complex than it is. But it's basically that if we have enough data, the distribution of the mean will be nearly normal. So here we are with a sample size of, let me look at the question, 150. 150 sample size? Well, the 150 sample size, as long as it's randomly collected, and I believe these are salmon right here, 150 salmon is less than 10% of all salmon that exists, and we're measuring the amount of murex in these farm salmon to see if there's issues. Well, it looks a little weird, tiny bit askew. Well, you know what? With it being a little skewed, the distribution of the mean, sample mean, will be more normal and tighter, and a sample size of 150 is more than large enough such that the distribution of the mean will be nearly normal. Once again, we're using an idea of large enough right here with the central limit theorem to let us know that we are good. From here, it simply comes down to doing the mathematics to find the answer. We need to plug in the sample size and find the standard error. Here's the sample size, here's the standard deviation, and here's the standard error. That becomes the denominator of the equation down here to standardize the difference. Here's the difference between our sample mean. The sample mean was 0.0913 murex in the fish. The hypothesized value was 0.08, and the standard error is right here, leading to a t statistic of 2.8. These are basically z's. They're not. They're basically. And since they're basically z's, if you think about it, is this pretty weird? Close to a z of 3, right? Yes, it'd be pretty far off the curve. The p-value right here for seeing a t at this or greater is super duper small. Try using software yourself to find this. What would the next decimal be when you enter this into an applet? So the t with 149 degrees of freedom, and you make sure to have the degrees of freedom, then you enter in the t, and since we're doing a greater than test, we're trying to see what is the probability that the murex would be this much or higher given 0.08 murex is the truth. You want to find the next decimal over here on software. Make sure to have your t-applet pulled up if you're trying to do this. Find out what the next decimal will be. We usually don't carry out that much precision. What would it be? What we need to know now, after we know the p-value, is how to determine these results. Well, interpreting your results, which is key. We need to write the following. I either reject or do not reject the null. If your teacher wants you to say fail to reject, say that instead. because my p-value is at or above / below, but first is below / at or above 0.05. Let's put alpha rather. This means I do have evidence / do not have evidence for my alternative that blank. Okay, now this is a lot. Everything I'm highlighting right here would have to be chosen or changed. I'll highlight some more in a second right here to make this super clear, but this is usually where students get stuck writing this out, and it only comes with practice. So we'll put this right here as one thing. Write this down. This means, here we go right here. We're going to do an example. Color coding this to help out. When you reject, it's because your p-value is below alpha and you do have evidence for your alternative. When you do not reject or fail to reject, statisticians will say your p-value is at or above alpha and you do not have evidence for your alternative because you do not reject the null, you do not have evidence for your alternative. This value right here, your p-value is just your p-value. Your alpha value needs to be your alpha right here. So make sure to put your alpha right there where I've highlighted that. These are not all the same value. It's just you will need to fill these out. Fill these out right here. How would this sound? Well, let's look at a question up here. We just got a very low p-value for this test. The test we just got had a p-value of 0.00, we're going to call it 0.003, just for rounding purposes, 0.003. So we know what goes in the p-value, 0.003. Unless otherwise stated, statisticians use an alpha level of 0.05. First thing to do, look at your p-value. Is it below 0.05? Yes, let's put it right there. So this puts us on the green path because the p-value is below 0.05. The only other things we need to know right now are going to be the alternative and the null, and then we can say this full thing. Well, the null hypothesis for this question was that the true mean level of Murex, not proportion, the true mean level of Murex is equal to 0.08. The alternative we were looking for evidence for is that the true mean level of Murex is greater than 0.08. So now you simply input a lot of this information to the problem. Take a look as we read it. I reject the null that the true mean level of Murex is equal to 0.08. Again, I just read this right here and put it right there. I reject the null that the true mean level of Murex is equal to 0.08 because my p-value of 0.003 is below my alpha of 0.05. This means I do have evidence for my alternative that the true mean level of Murex in these fish is greater than 0.08. Once again, practice and try writing this down. It only comes with practice, knowing this pathway right here, and remembering things like when the p-value is low, reject the null. When the p-value is high, just let it fly. Just let it be, don't reject it. When the p-value is low, reject the null. When the p-value is high, just let it fly. Don't reject it. Let it be. So, once again, I reject the null that the true mean level of Murex is equal to 0.08 in these fish because my p-value of 0.003 is below my alpha of 0.05. This means I do have evidence for my alternative. The true mean level of Murex is greater than 0.08. One last part of this. Intervals and tests do a lot of the same things for us. When it comes to an interval in a test, you can actually perform the two-tailed test by looking at an interval. This is because a two-tailed test visually looks like this, the area in the outside. And an interval looks like this, with the area in the inside. Any value believable for a 95% confidence interval contained in the interval would not be rejected on a two-tailed test. The p-value would not be small enough. So a 95% confidence interval can actually give us believable values that we would not reject at the 0.05 alpha level on a two-tailed test. So once again, going into a little more detail, confidence intervals are a great way to just do a statistical test. It's because 1 minus the level of confidence can be used as an alpha level. So remember how I said 95% confidence? Well, if you do 100% out of that, you're doing a 5% alpha on the two-tailed test. There's the 5% alpha on a two-tailed test. Change that. Well, if you did 90% in the center, 90% in the center would lead to a 10% alpha. So this would be 5% here on this tail and 5% here on this tail, leading to a alpha of 10% and 90% in the center. So you can approximate any sort of alpha. Usually we use 5% alpha, so usually you would see 95% confidence. And think about this. Here's results. Well, we would reject this at the 0.05 level. We would reject on the two-tailed test 33% as the truth. Because here's the two-tailed test in statistical software. First one is the does not equals, the next one is the greater than, and the less than. The does not equals uses the absolute value around it. So we would reject it at the 0.05 level, but we would not reject it at the 0.03 level. So the first interval right here is going to be a 95% confidence interval, and 33 is not contained in it. This one, 96%, not contained in it. But when you get to the 97% confidence interval, which would have an alpha level equal to 0.03, there's the 97%, and there's the alpha of 0.03 you would subtract if you want to go in reverse. It contains the value because we can see the p-value is above 0.03, it's above 0.03, and so you can't reject it in a 97% confidence interval on the two-tailed test. Very important to know things like this, that we can use confidence intervals to do statistical tests. And one last thing we should know is we can pick any level of alpha we want. When it comes to doing statistical tests, it's when the p-value is below the alpha right here. So what are some common levels of alpha that are used? 0.01, 0.05, 0.001. Here's the thing. Lowering your alpha makes it harder to reject the null. You're asking for more evidence because your p-value has to be lower. Increasing the alpha makes it easier to reject the null. We'll examine later how this can lead to more error when doing a test. So very important, remember the steps when doing your test. Make sure to write out your null and alternative, be able to read it as a sentence. Next, be able to do the mechanics and check the conditions. Find your p-value, and then interpret your results. You'll be able to do statistical tests.